Hello, welcome to the ME475 bike frame analysis. My name is Eric Skutnick and my partner is Lance Hayner.
The given frame and dimensions are shown in the picture on the left. The 3D model is shown to the right, and below that is the standard beam element model. Our reference frame is made of stainless steel with a Young's modulus of 193 gigapascals, a yield strength of 207 megapascals, and an ultimate tensile strength of 586 megapascals. The alternative material that we investigated was aluminum, with a Young's modulus of 71 gigapascals, a yield strength of 280 megapascals, and an ultimate tensile strength of 310 megapascals. The outer diameters of the tube sections are shown in the table on the left. The thickness for each tube in the reference steel frame and the aluminum frame is 0.8 millimeters. We also investigated an alternative design with 3 millimeter thick tubes. On the right is a table that shows the weight for the frame and the fork for each design. We considered two loading scenarios in this project. For the frontal impact scenario, the rear dropouts were fixed and 100 newtons was applied to each front dropout in the negative X direction. For the drop scenario, the seat and the handlebars were fixed and 100 newtons was applied to each dropout in the Z direction. ANSYS was used to perform FEM simulations. Modal analysis, harmonic analysis, and eigenvalue buckling analysis was performed for each frame using standard beam elements. Static structural analysis was performed for each frame using a 3D NX model. Fatigue was then analyzed in the static structural analysis.
For the front impact harmonic analysis, to simulate a rider, there was a 600 Newton force on the seat, 50 Newton force on the pedal, and 100 Newton force on the handlebars. Harmonic analysis was performed in the x-axis of the pedal joint. For this scenario, aluminum had the highest frequency response and the thicker steel had the lowest frequency response. The same loading conditions were used to simulate a rider in the drop impact scenario. For this harmonic analysis, it was performed in the y-axis on the seat joint, and aluminum had the highest frequency response while thicker steel had the lowest frequency response. Here are the results from the buckling and fatigue analysis. For this loading condition, the buckling safety factor was an adequate amount, with aluminum being the lowest and thicker steel being the highest. For the fatigue scenario, aluminum and the steel reference frame did not have infinite life, while the thicker steel for both loading conditions showed that it did have infinite life. For all these results, aluminum and the steel reference frame were pretty similar for each different scenario, front and drop. For the validation, the stress we saw from the ANSYS analysis was similar to those in the given reference paper, leading us to believe that this was a correct analysis. Although we did get a high buckling safety factor for both scenarios, this might be due to the loading conditions and the bounding conditions that we applied. Changing these and changing the thickness of the tubes might create a more accurate analysis.